In section 3.4, we introduce our newest integration technique of what we call partial fractions. Now again, we can see here that we've been developing this large list of different approaches that we can take whenever we come across an integral. And it's very important to note that each of our previous techniques had some instances, perhaps, where it might have seemed a little bit better to use that particular technique. Obviously, things like trig identities are very useful if I come across an integral with a lot of trig in it. Things like trig substitutions we saw were easy to implement when potentially I had some things with square roots. We saw that use substitutions back in Calc 1 were able to be used when we could see a function and its derivative inside of the integrand. And with partial fractions, what we'll see is that it's specifically a technique that's kind of like a fancy algebra technique. It is specifically going to be dealing with functions that are of the form of a polynomial divided by another polynomial. And so we'll see kind of how this works as we take a look at the start of 3.4 in our opening motivation. So at the start of the 3.4 notes, we can see this motivating example that is actually going to be an integral of a polynomial being divided by another polynomial, as we just mentioned. So the question that we're really going to have, though, is that if I have something like this and it can't be done, can't integrate this with any of those old techniques, how might I actually go about doing this? Well, I'm going to go ahead here and just show you a little bit about how I would actually perform some weird algebra here to go ahead and make this a whole lot simpler to work with. Now, this starting step that I'm going to take, again, is purely an algebra step, but it is a strange one. So I'm actually going to go ahead and I'm going to mark this equal sign here as kind of the equal sign that's in question. This is the one that'll be a little bit confusing. So why would these two things be equal? Well, watch what I'm about to do. I'm going to claim that this big fraction that I have right here is actually equal to the sum of these three smaller fractions. Now, you could easily go ahead and double check on your own that if you found a common denominator between these three fractions, you added everything together, you would indeed return to where I started here. Of course, the question is, how did I know that these were three fractions that made this piece? For the moment, I'm going to ask you to kind of hold off on that question and instead focus on why is it useful to have this be broken up in this way. What you might see now is that I could easily go ahead and separate this into three different integrals. And if I do this, as long as each one of these is easy to evaluate, then it should be pretty easy to come up with a final answer to the question. My first integral here, I can see, is going to turn into a natural log of absolute value of x. Over here, I'm going to end up with a, let's see, this would look something like a natural log of 2x plus 1, but it's not quite right. Double check really quickly with the derivative and see that this is not actually the complete derivative over here. Can you tell what I might need to adjust with? Well, yeah, you might notice that if I take the derivative of this, I'm going to have an extra times 2 that pops out from the chain rule. And so to protect against that, I'll put a 1/2 in front. I can also then see over here at the very last term, I'm going to have a natural log of absolute value of x minus 1. And of course, don't forget at the back, plus c. It's extremely important to remember these absolute value bars here when I'm doing these antiderivatives that involve logarithms. Now, again, this seems like, wow, what a great result. But, of course, the big question is, how did I know to go from that big fraction to those three smaller ones? And so we'll talk about in this section kind of like an algorithm to determine these smaller fractions that we can try to work with. Now, I'm also going to take a look down here on this integral and start to see about some comparisons that we can make between the integral up above and the one down below. Because you'll actually see in a moment that my starting approach here is going to be very different. First, I'll start by noting something important. We are going to refer to this type of rational expression as a proper rational expression. And the way that I am going to distinguish whether it's going to be proper is I'm going to look at these leading exponents that I have up here, right? This 2 and this 3. And I'll notice that since the degree on top is smaller than the degree on bottom, or if it was the same size, then I would call that a proper rational expression. Notice that down here I have 3 over power 1, and so this is what I would refer to as an improper rational expression. So when I come across an improper rational expression, my general approach is going to be a bit different. I'm going to actually go ahead and proceed, and I'll say we will proceed with a polynomial long division. If this is an improper rational expression, I can perform a polynomial long division and then see what I can do with the result. So it may have been a while since you've done one of these polynomial long divisions, but this is the way I like to think about it. I'm going to take the piece that I'm dividing right here, and I'm going to start to write it underneath my kind of division symbol that I have set up. So I have this x cubed. I'm actually going to go ahead and, just for the sake of spacing, put in 0x squareds, and then I have 1x, and I'll also put in a plus 0. So I kind of put in these placeholders. You don't have to, but I think it makes things nice. Over on the side, I'm going to have an x minus 1. And then recall that I'm looking for something that I can put up top. So when I multiply it to x, it creates x to the third. So I'm going to go ahead and state, well, how about x squared? That would work perfectly. If I take x squared and multiply it through here, I'm going to get x cubed minus an x squared. And I need to subtract this from what I have up above. These first two terms would hopefully cancel out if I've done things correctly. And so I can see here I'm going to be left with 0x cubes. I'll be left with 0x squareds minus negative x squared. So it's going to be a positive 1. And all the rest of my stuff I kind of just carry down. And now we just rinse repeat. So what can I multiply x by to create an x squared? Well, that would be I multiply by an x. And when I do that, I'm going to get an x squared minus an x, and I need to subtract this from what I have. First two terms cancel out. I'm going to be left with 2x plus 0. Rinse repeat. What can I multiply x by to generate 2x? Well, that's going to be plus 2. And when I distribute that 2 in there, I'm going to get a 2x minus a 2. I need to subtract that from the total, and so I'm going to end up with 2 left. This piece right here is my remainder. So what this tells me is that x cubed plus x over x minus 1 is equivalent to my red polynomial piece that I have up top, but plus this actual extra remainder, which is 2 left over out of what I was dividing by. So if I wanted to integrate what's on the left here, that's equivalent to integrating what's on the right. But notice that integrating the right is a lot simpler. So I'll write down here that my integral that I was looking for is actually equal to the integral of x squared plus x plus 2 plus 2 over x minus 1. And to integrate that is a breeze, because I'm going to get a 1/3 x cubed plus a half x squared plus a 2x plus 2 natural log absolute value x minus 1, and don't forget, plus c. So using this polynomial long division, again, on an improper rational expression is a great way to try to go ahead and determine what this antiderivative is going to be. So if we can kind of summarize what we've seen so far, on the next page I'm going to provide us with a general outline that we're going to attempt to follow in this section. It's going to ultimately come back to the idea of what we do if I have a proper or an improper rational expression, that is, a polynomial over a polynomial. So if I have an improper rational expression then we will do a polynomial long division. However, if we have a proper rational expression, remember that means the degree on the top of the fraction is either smaller than or the same size as, I misstated that. Proper rational expression would be that the degree on top is smaller than the degree on bottom. Improper, the degree on the top is either the same or larger. Then I'll be able to break that apart into these two camps. So proper rational expression, if the degree on top is smaller, then I will go ahead and I will take that, oops, this should say expression, but I will take that proper rational expression and rewrite it as a sum of its partial fractions. So let me just go back through each of the previous examples to see how they kind of correspond to what we've written here. Okay, we'll see that again if I have an improper rational expression, that is, the degree in the numerator is bigger than or the same size as the denominator, then I will go ahead and perform a polynomial long division like we did here. But if I have a proper rational expression, the degree on the top is smaller than the degree on the bottom, then I will go ahead and try to break that apart into these smaller fractions, what we call partial fractions, that make up the larger fraction. And so that second step of the outline is really going to be concerned with how I determine this blue equal sign, or how do I move from one step to the other. So we're actually going to spend most of our time in this section focusing on how I make this transition across the blue equals, because hopefully polynomial long division is something that you've seen before, and with a little bit of practice you can quickly refresh on. In the videos to come, we're going to see that we're actually going to break down this approach into 4 different kind of cases that we'll be able to take a look at to try to help understand how I can create these partial, smaller fractions that add up to this one overall larger fraction.